We've been looking at graphing our quadratic functions, and we've looked at them in two different forms. We've looked at them in what we call standard form, which is f of x equals a times x minus h squared plus k. In this form, hk is your vertex. It's either your lowest point or your highest point on the graph. It's where your graph changes directions. The axis of symmetry is x equals h. If a is positive, your graph opens up and you have a minimum. And since your graph opens up, your domain would be from negative infinity to positive infinity. Your minimum, since it's a minimum, you're going to start at the lowest y value, which would be your k, your vertex, and go to positive infinity. If a is negative, you're going to open down, and you'll have a maximum. And so your domain will be negative infinity to positive infinity, but your k value, your y value for your vertex is your highest point. It's your maximum. So your range is from negative infinity to positive infinity. We also have another form, what we might call our general form, which is f of x equals ax squared plus bx plus c. In this case, our axis of symmetry is x equals the opposite of b over 2a. The vertex then is that x value, the opposite of b over 2a, and then we have to substitute it into our function to find our y value. If a is positive, the graph opens up and we have a minimum. If a is negative, the graph opens down and we have a maximum, and we do our domain and ranges just the same. So let's look at this equation, and we want to go through and find our values, and we want to graph this. So as we go through to look at our values, the first thing we want is our axis of symmetry. So x is equal to the opposite of b, which is a negative 2 over 2 times a, which is 3. Now the opposite of a negative is a positive, and that would be 1/3. So our x value for our vertex is going to be 1/3. But our axis of symmetry is x equals 1/3. Now, to find out what our y value is, we would have to substitute that in. And so we would want to find f of 1/3. So we have 3 times 1/3 squared minus 2 times 1/3 minus 4. So that would be 3 times 1/9 minus 2/3 minus 4, or 1/3, because our 3 will cancel or reduce. So we have 1/3 minus 2/3. And let's just go ahead and change this fourth to thirds so that we have our common denominators. So 4 would be 12/3. 12 divided by 3 is 4. So it would be 12/3. So that gives us -1, negative 13/3. So our vertex then is going to be 1/3, negative 13/3. Now, as we go to graph this, graphing is not always exact. So as we go through to do these values, then we're going to have to just estimate where these values are. So here's 1, it'd be about 1/3, and then negative 13/3. Well, 3 goes into 13 4 times with 1 left over, so that's negative 4 1/3. And so there would be our vertex. Now we could have drawn our axis of symmetry through where x equaled 1/3 from about here. And going down hung in there. So we would have then our axis of symmetry, and we have our vertex negative 1/3 or 1/3 negative 13/3. But it's not exact. Now we'd like to get some other points, and what we've discussed is that where we cross the y-axis is a good place, and then where we cross the x-axis. And so those are points that are fairly easy to get. If we want to get the y-intercept, let's go ahead and do the y-intercept first this time. And to get the y-intercept, we simply substitute in 0 for x. So we're going to find f of 0. Well, that means every term that has an x would be 0. So that's going to be negative 4. So our y-intercept will be 0, negative 4. Now, if we go to our graph and we plot that, 0, we're going to be at negative 4. Now, that's 1/3 units from our axis of symmetry. And so what we would do is we would go the same distance on the other side, which would be to 2/3. And we would put our point. Now, if we can get the x-intercepts, to do that, we take our function and we set it equal to 0. So our function was 3x squared minus 2x minus 4 equals 0. And we could try to factor it, or we can go ahead and use our quadratic formula. So x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be a positive 2 plus or minus the square root of 4. We have a negative times a positive times a negative. So that's going to be a positive 48 all over 6. Okay, and then that would give us 2 plus or minus the square root of 52 over 6, which would be 2 plus or minus, now 52 is 4 times 13, so the square root of 4 is 2. Square roots of 13 over 6, and we can reduce all of those by 2. So we would end up with 1 plus or minus the square root of 13 over 3. Now, when we start plotting that on our x-axis, this is where we're crossing the x-axis, we may not know exactly where those points are. We can reason them through, and then we're also going to use the calculator. But the square root of 13 is somewhere between 3 and 4. Square root of 9 is 3, square root of 16 is 4. So it's a little bit more than 3. So if we have 1 plus a little bit more than 3, then we have just a little bit more than 4 divided by 3 would be a little bit more than 1. So it's going to be 1 plus something. We'll just say 1 plus. If it's 1 minus a little bit more than 3, then that would be about negative 2 something. And so this is going to be just a little less than 1. And so it might be about 0.8 or so. But we could go through and it would be a negative. And so we could go through and just kind of estimate the values, because when we plot them on our graph, we can't be exact. But let's go to our calculator and just see what we would have. If we have 1 plus the square root of 13. And we close our square root. Now, we didn't put our parentheses to begin with, which we should have. So let's go back to the beginning. Maybe we can go back to the beginning. Let's just clear it then. Well, it's real nice. It froze up on us. Okay, let's put our parentheses this time. 1 plus the square root of 13. Now we have to close the square root, and then we close the parentheses for our numerator divided by 3. Okay, that equaled the 1.5. And if we went back and we did it parentheses 1 minus the square root of 13, close our parentheses, divided by 3, we get negative 8.68. So as you saw, we were a little bit more than 1, and then around negative 0.8, just a little bit less than that as we went through. So if we wanted to put our values down then, we're going to plot them. We had 1.5 and negative 0.8 something. So we can go to our graph and we can plot those points. So we had on the y-axis, we had about 1.5 and negative 0.8. And then we can draw our parabola. And we can graph our points. And we saw that we had a minimum. So our domain is negative infinity to positive infinity. Our range was that point, which was our negative 13/3. And we go to positive infinity. All right, now there's some other things that we can do. Just by looking at our equation, we can determine if we have a maximum or a minimum. If we have f of x is equal to 2x squared minus 8x minus 3. And we want to know, do we have a maximum or a minimum? Well, since a is positive, since 2 is greater than 0, that means that we open up, so we have a minimum. And sometimes that's all that you need to know is, do you have a maximum or a minimum? And that's how you would know, is by looking at a. If a is negative, then it's going to open down and you would have a maximum. If we wanted to find the minimum and where it occurs, now the minimum is your y value. Where it occurs is the x value. So it's going to occur at x is equal to the opposite of b over 2a. So in this case, it's going to occur at the opposite of negative 8 over 2 times 2, which is 8 over 4, or 2. So that's where it's going to occur. It occurs on your axis of symmetry. If we want to know what it is, then we have to substitute that back into our equation. We'd have 2 times 2 squared minus 8 times 2 minus 3. So we have 2 times 4 minus 16 minus 3, or 8 minus 16 minus 3. So negative 8 minus 3, negative 11. So our minimum is negative 11. It occurs at x equals 2. And if we wanted to write it as an ordered pair, we could, of 2, negative 11. Then if we wanted to give the domain and range, our domain is going to be from negative infinity to positive infinity. Our range We have a minimum, so negative 11 is our lowest point. So we would start there and go to positive infinity. Okay, let's say that we're asked to give the domain and range. And all that we know about our function is that the vertex is at -3, -4, and we know that our graph opens down. Well, if our graph opens down, it means this is a maximum. So our domain will be from negative infinity to positive infinity. We can use all real numbers for our x's. Now our range, that highest point is the y value of our maximum. So we're going to go from negative infinity all the way up to our y value of -4. And that would be our range. So you can give the domain and range different ways given different pieces of information. You might be asked to write an equation. Let's say we want to write an equation in standard form. And for a graph that has the same shape as f of x equals 2x squared, and it's got a vertex at 7, 4. Now, if you remember back when we did all of our transformations, the number here, our A, is what determined how wide we opened or how narrow we opened. It dealt with the stretching and the shrinking. So if we're going to have the same shape, then it means it has to have this same coefficient as our A. Standard form, if you remember, is where it's in the form of f of x equals a times x minus h plus k. So really all we're needing to know is where our vertex is. We already know what a needs to be. So if we go back and we look at this one, if we can find it, there we are. So that means our a is going to be the same. So it's going to be f of x is equal to 2, then times, well, x, this is our h, so x minus 7 squared plus 4. So that would be the same equation. It would be the equation in standard form that had the same shape as this graph, but it had a different vertex. And we could go through and actually just check that. Let's just check it. If we graphed y equals 2x squared, and then let's also graph y equals 2 parentheses x minus 7 plus 4. And let's go ahead and just graph both of those. So you can see from these that we've got the same shape. We've just moved our vertex over to 7, 4, which is what we were wanting to do. But the shape stayed the same. Okay, let's look at one more. And in this case, we want to have the same shape as f of x equals 3x squared. And we want to have a maximum of -7 at x equals 5. We want to have a maximum. Okay, now if it's a maximum, then that means it's going to open down. So that means that we're going to have to use a -3. So our equation's going to be f of x is equal to -3. Now, the maximum's -7. That's our y value, so that's our k, and our x value is our h. So x minus h squared plus k. Now, this will still have the same shape. It's just going to open in the opposite direction because we wanted it to be a maximum at -7. Okay, let's look at a problem that helps us see where we might use this idea of the maximum and the minimum are axes of symmetry and how we would go about using this. Here we have a problem where a man has 200 feet of fencing to enclose a rectangular plot that borders a river. Find the length and width that will maximize the area. So he's got a rectangular plot, and he's going to put it, but there's going to be a river flowing on one side, so he's not going to need to fence that side. But he's going to fence the other sides. So he's got 3 sides to fence. And he's going to use a rectangle. So we have this side that's a width, this side that's a width, and then we've got our length. And as he changes that, then it changes his area. You know, he could have 1 foot here and 1 foot here, which would leave him then 198 feet here. But his square area would only be 198. Well, if he came out 2 foot here and 2 foot here, then that leaves him 196. And so 2 times 196 would be 392. Is that correct? Yeah, 392. And so he would have a lot more area. So as he changes his dimensions, he changes his area. Well, we know that our formula for area is length times width. So that's what we're going to start with. That's what we're wanting to maximize. Well, what we know here is that if we added this up, his length plus his 2 widths, that's going to be his 200 feet of fencing. So if we wanted to write this all in terms of one variable, then the length would be 200 minus 2w. So we're going to substitute that in for the length, 200 minus 2w times w. Then that would be a formula that would give the area for this rectangle. And if we distributed, we would have 200w minus 2w squared. And we could switch that around. Now, what we want is what his length and width need to be so that he'll have the maximum area. We know that this is going to be a maximum because it's a quadratic that opens down. We know the maximum will occur on the axis of symmetry. So all we need to get is our axis of symmetry, which in this case we would say W is equal to the opposite of B over 2A. Or negative 200 over negative 4, which would give us a positive 50. So for the maximum area, then the width would need to be 50. To find out what the length is, well, we have a little formula here to substitute into. We can find out the length is equal to 200 minus 2 times W, which was 50, or 200 minus 100, which is 100, not 200, but it's 100. So he needs to have a width of 50 feet and a length of 100 feet. And that will give him an area then of 5,000 square feet, which would be the maximum area. And so you can use it in a lot of problems where you're needing to find maximums and minimums.